What if I told you that black holes, those cosmic monsters that devour light itself, might not be the most terrifying objects in the universe? What if something far stranger, far deadlier, and far more disturbing to our understanding of reality exists in their place? Meet the Gravastar, a theoretical object so extreme that it makes black holes look tame by comparison. Imagine a bubble of warped space-time, where the fabric of reality itself has crystallized into an impenetrable shell. Inside this shell, nothing, an empty space, true nothingness, a void more perfect and more terrifying than anything we thought possible. Outside, a surface where time stops, gravity becomes infinite, and the laws of physics scream in protest. Today, we're venturing into the bleeding edge of theoretical physics, where Einstein's equations predict something that Einstein himself would have found impossible. We're exploring gravastars, gravitational vacuum stars, objects that could solve black hole paradoxes while creating entirely new nightmares for physics. These aren't just mathematical curiosities. If they exist, they're out there right now, masquerading as black holes, hiding a secret that could revolutionize our understanding of the cosmos. To understand why gravastars are so revolutionary and so terrifying, we first need to understand the crisis at the heart of black hole physics. For decades, black holes have been both triumph and torment for physicists, representing our greatest success and our most spectacular failure simultaneously. Einstein's general relativity predicts that when enough matter concentrates in one place, space-time collapses catastrophically. The result is a singularity, a point of infinite density where the laws of physics break down completely. Around this singularity forms the event horizon, the point of no return. Cross it and not even light can escape. It's poetic, terrifying, and according to our best theories, inevitable. But here's where things get uncomfortable for physicists. Stephen Hawking discovered that black holes emit radiation. They slowly evaporate. This creates the infamous information paradox. When a black hole evaporates completely, what happens to all the information about the matter that fell in? Quantum mechanics says information cannot be destroyed. General relativity says it must be. This isn't just a minor inconsistency. It's a fundamental contradiction between our two most successful theories of the universe. The singularity itself is another problem. In physics, infinities usually signal that your theory is breaking down, that you're pushing equations beyond their limits. Yet we accept that billions of these infinite points exist throughout the universe. Every black hole supposedly harbors a singularity where density becomes infinite. Space-time curvature becomes infinite, and our understanding becomes nothing. Enter Pavel Mazur and Emil Motola. In 2001, these physicists asked a radical question. What if nature abhors singularities? What if, at the very moment a black hole would form, something else happens instead? Something that preserves the external appearance of a black hole, but has a radically different interior. Their answer was the Gravastar, and it would challenge everything we thought we knew about extreme gravity. Imagine a massive star in its death throes. For millions of years, nuclear fusion in its core has fought against gravity, maintaining a delicate balance. But now the fuel is exhausted. Gravity begins winning, and the star collapses. In the traditional picture, nothing can stop this collapse once it begins. The matter crushes down to a singularity, and a black hole is born. But Mazur and Motola proposed something different. As the collapsing matter approaches the point where an event horizon would form, something extraordinary happens. The immense gravitational energy triggers a phase transition in space-time itself, similar to how water suddenly turns to ice, but infinitely more exotic. The collapsing matter doesn't crush into a singularity. Instead, it forms a shell, a thin, incredibly dense boundary where space-time itself has fundamentally changed its nature. This isn't ordinary matter anymore. It's matter in a state so extreme we have no earthly analogy. The closest comparison might be to a Bose-Einstein condensate, where quantum effects become macroscopic, but even that falls short of describing the alien physics at play. Inside this shell, something even stranger occurs. The interior doesn't fill with crushed matter or exotic particles. Instead, it enters a state physicists call de Sitter space, a region dominated by dark energy, the mysterious force causing our universe's acceleration. But here's the truly terrifying part. This isn't just empty space with dark energy. The interior exists in a fundamentally different state of being, where the very concept of particles, matter, and perhaps even existence as we understand it, breaks down. The pressure inside a gravastar is negative. It pushes outward rather than inward, exactly balancing the enormous gravitational pull trying to crush the shell. It's like a cosmic bubble that can never pop, a perfect equilibrium between forces that shouldn't be able to coexist. The result is an object that looks exactly like a black hole from the outside, but is fundamentally, radically, terrifyingly different on the inside. A gravastar consists of 3 distinct regions, each more bizarre than the last. Let's journey from the outside in, though be warned. This journey challenges not just our physics, but our very conception of reality. The exterior region extends from the gravastar's surface outward to infinity. Here, space-time behaves almost exactly as it would around a black hole. Light bends, time dilates, and any approaching matter experiences the same terrifying tidal forces. This is why gravastars could have hidden in plain sight. Every black hole we think we've detected could actually be a gravastar, and we'd have no way to tell from outside observations alone. The shell itself is perhaps the most fascinating region. This isn't a surface in any conventional sense. It's a boundary where the fundamental nature of space-time changes. The thickness of this shell is infinitesimal, perhaps only a few Planck lengths, the smallest possible distance in physics. Yet within this impossibly thin region, matter exists in a state beyond our current understanding. The matter in the shell isn't composed of atoms or quarks or any particles we're familiar with. It exists in what physicists call a stiff fluid state, where the speed of sound equals the speed of light. This means any disturbance in the shell propagates instantly across its entire surface. The whole shell vibrates as one, like a single star-sized quantum object. The density here approaches the Planck density. The theoretical maximum density possible before space-time itself becomes meaningless. But it's the interior that truly defies comprehension. This region is dominated by dark energy, with a negative pressure so extreme it perfectly balances the shell's tendency to collapse. This isn't a vacuum in the traditional sense. It's not empty space waiting to be filled. Instead, it's space in a fundamentally different quantum state, where virtual particles behave differently, where the zero-point energy of quantum fields takes on alien properties. Some theorists suggest the interior might be causally disconnected from our universe, a pocket of space-time where cause and effect as we understand them cease to operate. Information that enters this region doesn't just become inaccessible. It might cease to exist in any meaningful sense. It's not destroyed. That would violate quantum mechanics. Instead, it enters a state where the very concept of information no longer applies. The connection between gravastars and dark energy opens a Pandora's box of cosmic implications. Dark energy, the mysterious force accelerating our universe's expansion, makes up 68% of the universe's energy density. Yet we have no idea what it actually is. Gravastars might provide a crucial clue. Inside a gravastar, dark energy isn't just present. It's concentrated to densities that shouldn't be possible. While dark energy in our universe has a minuscule density, barely enough to overcome gravity on cosmic scales, inside a gravastar, it reaches densities comparable to nuclear matter. This concentration could teach us about dark energy's true nature, revealing properties invisible at cosmic scales. Consider the implications. If gravastars exist, they're laboratories where dark energy is compressed by factors of 10^120. That's a 1 followed by 120 zeros. This compression might reveal whether dark energy is truly constant, as Einstein's cosmological constant suggests, or whether it varies under extreme conditions. The answer could determine the ultimate fate of our universe. Some theorists go further, suggesting gravastars might actually produce dark energy. As matter falls onto a gravastar's surface and undergoes the phase transition, it might generate the very dark energy that fills our universe. If true, gravastars aren't just objects within our universe. They're actively shaping its evolution, pumping dark energy into the cosmic fabric like hearts pumping blood through cosmic veins. This raises a terrifying possibility. What if the accelerating expansion of our universe isn't driven by a uniform dark energy field, but by countless gravastars throughout the cosmos, each contributing to the cosmic acceleration? Our universe's fate, whether it expands forever, tears apart in a big rip, or transitions to a new phase, might depend on these hidden monsters masquerading as black holes. There's an even more radical proposal. Our entire universe might exist inside a gravastar. The observable universe's properties, its flatness, its acceleration, its boundary, match eerily well with what we'd expect if we lived within a gravastar's interior. This gravastar cosmology suggests the Big Bang wasn't a beginning, but a phase transition. The moment our parent star collapsed, and our universe was born within its shell. It's a hypothesis that sounds like science fiction, but emerges naturally from the mathematics. The most frustrating aspect of gravastars is that they're nearly impossible to distinguish from black holes using conventional observations. They have the same mass, the same gravitational field, the same effect on nearby matter. Light behaves identically around them. Matter spirals in with the same patterns. By design, gravastars are perfect black hole imposters. But nearly impossible isn't the same as impossible. Scientists have proposed several ways we might unmask these cosmic chameleons. The key lies in finding signatures unique to gravastars, phenomena that black holes, with their event horizons and singularities, cannot produce. Gravitational waves offer our best hope. When two black holes merge, they produce a characteristic ring-down, a gravitational wave signal as the merged black hole settles into its final state. But gravastars would ring differently. Their solid shells would vibrate like struck bells, producing overtones and harmonics impossible for black holes. The LIGO and Virgo detectors have already detected dozens of merger events. Hidden in that data might be evidence that some of these black holes were actually gravastars. In 2016, the first gravitational wave detection, GW150914, showed unexpected echoes, faint repetitions of the main signal arriving seconds later. While most physicists attributed these to noise, some theorists suggested they could be gravastar signatures, gravitational waves bouncing off the shell's interior surface. Subsequent detections have shown similar echoes, though their significance remains hotly debated. Another smoking gun would be matter bouncing off a gravastar's surface. When matter strikes a black hole's event horizon, it vanishes forever. But matter hitting a gravastar's shell would release a final burst of energy, a death cry that black holes cannot produce. Advanced telescopes might detect these flashes, particularly in X-rays and gamma rays, revealing gravastars hiding among supposed black holes. The Event Horizon Telescope, which produced the first image of a black hole's shadow, might also distinguish gravastars. While the shadow would look similar, subtle differences in the surrounding accretion disk's behavior could reveal the presence of a solid surface rather than an event horizon. The plasma swirling around a gravastar might be slightly hotter, slightly brighter, exhibiting turbulence patterns impossible around true black holes. Perhaps most intriguingly, gravastars might explain some cosmic mysteries already puzzling astronomers. Fast radio bursts, powerful millisecond flashes from deep space, could be matter-striking gravastar surfaces. Some gamma-ray bursts show unusual precursor emissions that make sense if they're caused by gravastars rather than black holes. Even dark matter might partially consist of primordial gravastars formed in the early meat universe. Gravastars represent more than just an alternative to black holes. They're a bridge between quantum mechanics and general relativity, potentially resolving contradictions that have plagued physics for decades. Understanding them requires venturing into the quantum realm, where space-time itself becomes granular, uncertain, alive with quantum fluctuations. At the gravastar's shell, quantum effects become dominant. The matter here exists at the Planck scale, where the smooth space-time of general relativity breaks down into quantum foam, a seething, probabilistic maelstrom where virtual particles constantly appear and disappear, where space-time itself fluctuates wildly. Yet somehow, These quantum fluctuations stabilize into a macroscopic structure, creating a stellar mass quantum object. This shouldn't be possible. Quantum effects typically average out at large scales. That's why we don't see cars tunneling through walls or planets existing in superposition. But gravastars might be different. Some theorists propose they're essentially giant quantum bubbles, maintaining quantum coherence across stellar distances through mechanisms we don't yet understand. The implications for quantum gravity are profound. String theory, loop quantum gravity, and other attempts to unify physics make different predictions about gravastar properties. By studying gravastars, if we can find them, we might finally determine which approach to quantum gravity is correct. They're natural laboratories where quantum mechanics and general relativity are forced to coexist, revealing how nature reconciles these seemingly incompatible theories. The information paradox dissolves if gravastars replace black holes. Information isn't destroyed because there's no event horizon to cross, no singularity to reach. Instead, information becomes encoded in the shell's quantum state, preserved but transformed into forms we don't yet recognize. When a gravastar eventually decays, through processes that might take googles of years, this information could be released, maintaining quantum mechanics' fundamental requirement that information is conserved. Some researchers suggest gravastars might exhibit quantum properties on macroscopic scales. They could exist in superposition, being in multiple states simultaneously until observed. Pairs of gravastars might be quantum entangled, instantaneously affecting each other across cosmic distances. These ideas sound absurd, but they emerge naturally from taking quantum mechanics seriously at gravitational scales. Not all gravastars are created equal. Theorists have proposed a terrifying zoo of variations, each with unique properties that challenge our understanding of possible cosmic objects. These aren't just mathematical curiosities. If gravastars exist, these variations should exist too, populating our universe with objects beyond our wildest nightmares. First, consider size. While we typically imagine gravastars replacing stellar mass black holes, there's no fundamental limit to their scale. Microscopic gravastars, smaller than atoms, might have formed in the early universe when densities were extreme. These primordial gravastars could be dark matter candidates, invisible and undetectable except through their gravitational effects. Billions might pass through Earth every second, and we'd never know. At the opposite extreme, supermassive gravastars could lurk at galactic centers. The object at the Milky Way's heart, Sagittarius A, might not be a 4 million solar mass black hole, but a gravastar of unimaginable proportions. Its shell would encompass a volume larger than our solar system, containing enough dark energy to accelerate a small universe. Then there are nested gravastars within gravastars like Russian dolls of warped space-time. The interior of one gravastar could spawn another, smaller gravastar, which could spawn another, creating a fractal hierarchy of shells and voids. Each level would exist at different energy scales, possibly with different physics, creating pockets of reality with alien laws of nature. Rotating gravastars add another layer of complexity. Unlike black holes, which simply drag space-time around them, rotating gravastars would have shells with complex circulation patterns, creating gravitational fields that pulse and fluctuate. These oscillations could generate gravitational waves continuously, making them cosmic lighthouses broadcasting their presence across the universe. Perhaps most disturbing are charged gravastars, where electromagnetic fields become trapped in the shell's quantum structure. These objects would be surrounded by intense magnetic fields, billions of times stronger than anything on Earth, capable of tearing apart atoms from millions of miles away. Approaching one would mean death by magnetic disintegration long before gravity became a concern. Some theorists propose naked gravastars, objects where the shell has partially collapsed or never fully formed, exposing the dark energy interior to our universe. The consequences would be catastrophic. Dark energy would leak out, potentially triggering phase transitions in nearby spacetime, converting normal space into exotic states. A naked gravastar could theoretically destroy entire star systems, not through gravity, but by fundamentally altering the nature of space-time itself. One of the most heated debates about gravastars concerns their stability. Can these exotic objects actually exist in nature, or are they mathematical phantoms? Solutions to Einstein's equations that reality refuses to manifest? Critics argue that gravastars are fundamentally unstable. The balance between the shell's gravitational collapse and the interior's dark energy pressure is so precise that any disturbance, a falling asteroid, a passing gravitational wave, even quantum fluctuations, should destroy it. They liken gravastars to pencils balanced on their points. Theoretically possible, but practically impossible to maintain. The shell itself presents stability challenges. Matter at such extreme densities should undergo phase transitions, potentially catastrophic ones. Quantum effects could tunnel through the shell, allowing interior dark energy to escape. The surface might develop instabilities, rippling and buckling until the entire structure fails. Computer simulations show some gravastar configurations collapsing within microseconds of formation. But defenders counter with surprising findings. Some calculations suggest gravastars aren't just stable. They're more stable than black holes. The shell's quantum properties might provide a stabilizing mechanism, with quantum pressure preventing collapse, even when classical physics predicts doom. The dark energy interior could act as a cosmic shock absorber, dampening disturbances that would otherwise destroy the structure. Recent simulations using quantum gravity theories show gravastars surviving conditions that would destroy any conventional object. They can absorb massive impacts, survive near collisions with other gravastars, even withstand partial shell ruptures. In some models, damaged gravastars can self-repair. The dark energy interior sealing breaches like a cosmic immune system. The stability question has profound implications. If gravastars are unstable, they're cosmic bombs waiting to explode, each one containing enough energy to sterilize galaxies. The universe would be a minefield of potential gravastar detonations, any one of which could end civilization. But if they're stable, they're permanent features of our cosmos, immortal objects that will outlive stars, galaxies, perhaps the universe itself. If gravastars exist, they don't just change our understanding of collapsed stars, they revolutionize cosmology itself. Every assumption about the universe's past, present, and future needs reconsideration. Consider the early universe. Milliseconds after the Big Bang, when temperatures exceeded trillions of degrees and density approached Planck scales, conditions were perfect for gravastar formation. Primordial gravastars could have formed by the billions, smaller than atoms but more massive than mountains. These objects would still exist today, invisible and undetectable except through gravity, potentially explaining dark matter. The universe's large-scale structure might be shaped by gravastars. If they're common, their dark energy interiors affect cosmic expansion locally, creating bubbles of accelerated expansion throughout space. Galaxies might preferentially form in regions with fewer gravastars, where expansion is slower. The cosmic web, the universe's largest structure, could be a fossil record of primordial gravastar distributions. Gravastars could explain several cosmic mysteries. The universe's missing antimatter might be trapped in gravastar shells, isolated from normal matter. Cosmic inflation, the universe's initial exponential expansion, might have been triggered by a phase transition similar to gravastar formation. Even the Big Bang itself might have been a gravastar's birth. Our entire universe existing within a shell formed 13.8 billion years ago. The future becomes equally uncertain. If black holes are actually gravastars, Hawking radiation takes on new meaning. Instead of evaporating completely, gravastars might reach a minimum size where quantum effects prevent further shrinkage. The universe's far future wouldn't be empty space punctuated by evaporating black holes, but a sea of microscopic gravastars, quantum remnants preserving information about everything that ever fell into them. There's a darker possibility. If gravastars can undergo phase transitions, converting normal matter to shell material and regular space to dark energy-dominated interiors, they might be infectious. One gravastar colliding with a neutron star might convert it to another gravastar. This gravastar catastrophe could propagate through the universe, converting all matter into gravastar shells, leaving a cosmos of hollow shells surrounding voids, a universe that's literally empty inside. Beyond the physics, gravastars challenge our philosophical understanding of existence itself. They force us to confront questions about the nature of reality, information, and what it means for something to exist. Inside a gravastar, does space and time exist as we understand them? If the interior is causally disconnected from our universe, is it part of our reality or something else entirely? When matter crosses the shell and enters this alien realm, does it cease to exist in any meaningful sense? Or does it transition to a form of existence our physics cannot describe? The information question becomes philosophical. If information entering a gravastar becomes encoded in quantum states we can't decipher, is it preserved or effectively destroyed? It's like asking whether a book thrown into a fire is destroyed or merely transformed into heat. Light and ash, technically the information persists, but in forms that mock our ability to retrieve it. Gravastars blur the boundary between something and nothing. Their interiors aren't empty, they're filled with dark energy. But this dark energy exists in a state that defies our concepts of substance and void. It's a presence that manifests as absence, a fullness that appears as emptiness. Ancient philosophers would have been fascinated by objects that embody such contradictions. If our universe exists inside a gravastar, what does that mean for reality? Are we living in a pocket of existence fundamentally separated from a true reality outside? Is every gravastar a potential universe, each containing its own physics, its own possibilities, perhaps its own forms of life? The multiverse might not be parallel dimensions but nested gravastars, each one a cosmos unto itself. These objects challenge scientific materialism itself. Gravastars suggest that the universe's fundamental nature might not be matter and energy as we understand them, but something more abstract, information, quantum states, or mathematical structures that manifest as physical reality only under certain conditions. They hint at a universe far stranger than our ancestors imagined, where the distinction between real and unreal, possible and impossible, becomes meaningless. As I speak, scientists worldwide are hunting for gravastars. This isn't fringe science. Major universities, national laboratories, and space agencies are dedicating resources to gravastar research. The hunt involves theorists pushing mathematics to its limits, observers analyzing telescope data for telltale signatures, and experimentalists designing new ways to probe extreme gravity. The LIGO scientific collaboration has established working groups specifically to search for exotic compact objects, including gravastars. They're developing new analysis techniques to detect the subtle differences between black hole and gravastar merger signals. Every new gravitational wave detection is scrutinized for anomalies that might indicate gravastar involvement. The next generation of gravitational wave detectors, the Einstein telescope in Europe, Cosmic Explorer in the United States, and the space-based LISA mission, will have sensitivity to detect gravastar signatures invisible to current instruments. They'll hear the universe's gravitational symphony in unprecedented detail, potentially revealing gravastars through their unique gravitational melodies. Theoretical work is equally intense. Scientists are using supercomputers to simulate gravastar formation, evolution, and destruction. These simulations require modeling quantum gravity effects, dark energy dynamics, and exotic matter states simultaneously, pushing computational physics to its absolute limits. Each simulation takes months on the world's fastest computers, yet might represent only microseconds of gravastar time. New mathematical frameworks are being developed specifically to describe gravastars. These involve exotic branches of mathematics, non-commutative geometry, quantum information theory, holographic principles that barely existed decades ago. Young physicists are training in these esoteric fields, preparing to tackle problems their predecessors couldn't even formulate. Laboratory experiments, while unable to create actual gravastars, are exploring analogs. Scientists use Bose-Einstein condensates, superfluid helium, and optical systems to create analog gravastars, systems that mathematically mirror gravastar physics without the gravitational fields. These experiments provide insights into quantum effects at gravastar surfaces, stability mechanisms, and information encoding that would otherwise remain purely theoretical. As we stand on the brink of potentially discovering gravastars, we must confront the ultimate questions they raise. These aren't just scientific queries, but profound challenges to our understanding of existence, reality, and our place in the cosmos. If gravastars exist, what does it mean for the search for extraterrestrial life? Advanced civilizations might harness gravastars as ultimate energy sources, extracting dark energy from their interiors. They might use gravastars for cosmic engineering projects we can't imagine, creating pocket universes, manipulating space-time, or achieving forms of existence that transcend normal matter. The silence of the cosmos might not indicate absent life, but life that has transcended to gravastar-mediated forms of existence we can't recognize. What if consciousness itself is somehow connected to gravastars? Some theories of quantum consciousness suggest that awareness emerges from quantum processes in microtubules within neurons. If gravastars maintain quantum coherence on stellar scales, could they support forms of consciousness utterly alien to our experience? Could the universe itself achieve awareness through networks of entangled gravastars? The discovery of gravastars would force us to reconsider humanity's cosmic significance. We've already been humbled by learning Earth isn't the center of the universe, that our sun is ordinary, our galaxy unremarkable. Finding that even black holes, the universe's most extreme objects, are something else entirely would be another blow to our cosmic ego, yet it would also elevate us. A species barely out of the Stone Age, contemplating objects that challenge the universe's fundamental nature. Perhaps most profoundly, gravastars ask us what we're willing to accept as real. These objects emerge from our most successful theories, yet violate our intuitions about what should exist. They're predictions we didn't want, solutions we didn't seek, possibilities we'd rather ignore. But nature doesn't care about our preferences. If gravastars exist, we must expand our concept of possible, accepting a universe stranger than we're comfortable imagining. Gravastars represent everything terrifying and wonderful about scientific discovery. They're objects that shouldn't exist, yet might be everywhere. They're solutions to problems we didn't know we had, creating new mysteries deeper than those they solve. They promise to unite quantum mechanics and general relativity, while threatening everything we thought we understood about both. If you feel unsettled by gravastars, you should. These aren't comfortable objects that fit neatly into our cosmic catalogue. They're reminders that the universe doesn't owe us comprehensibility, that reality's true nature might be forever beyond human understanding. Every gravastar potentially harbors secrets that would shatter our worldview. Information encoded in quantum states we can't decipher, physics we can't access, realities we can't explore. Yet this terror contains profound beauty, that human minds can conceive of gravastars, that our mathematics predicts them, that our instruments might detect them. This is miraculous. We're cosmic infants, contemplating objects that embody the universe's deepest mysteries. We're reaching toward truths that might transform not just our science, but our species' entire trajectory. As you go about your day, remember that gravastars might be all around us. That ordinary-looking star might be a gravastar. The black hole at our galaxy's center might be a gravastar. You yourself are made of atoms that might have passed through gravastar shells, been encoded in their quantum surfaces, existed in their dark energy voids. We might be living in a gravastar universe, every observation we make filtered through the physics of an impossibly vast shell. The hunt for gravastars has just begun. In the coming years, new observations will either confirm their existence or constrain their properties. Each gravitational wave detection, each telescope observation, each theoretical breakthrough brings us closer to the truth. We're living through one of the most exciting periods in physics history, when the universe's most fundamental secrets hang tantalizingly within reach. What do you think? Are gravastars real, or are they mathematical mirages that will evaporate under closer scrutiny? Do they solve black hole paradoxes or create new ones? Are we ready for a universe where such objects exist? Or would their discovery break something fundamental in how we understand reality? Share your thoughts in the comments below And remember, in a universe that allows gravastars, anything might be possible. Keep looking up, keep questioning, and never stop marveling at the cosmic horror and wonder that surrounds us. The universe is under no obligation to make sense to us, but it has given us the gift of minds capable of confronting its mysteries. Whether gravastars are real or not, the journey to understand them reveals the beauty, terror, and ultimate mystery of existence itself.